All right, we got a tough one here. Phosphate, PO4, 3 minus. We need to figure out the Lewis structure and these molecular properties. So before we can figure out any of these geometric properties, we need to get this Lewis structure down. So I'm going to keep plugging along in the way that I always have with Lewis structures. I'm going to count up my valence electrons. 5 from phosphorus, 6 times 4 is 24 from oxygen. And I have a 3 minus charge. So that means I'm going to add 3 electrons. From that, I get 32 total valence electrons to make the structure. Now, I'm going to go ahead and arrange the atoms as symmetrically as I can on the paper. Put the phosphorus in the middle and the oxygens around. And I'll start off, just like I had before, drawing a single bond to all of the atoms from the central atom. Now let's remove the electrons from that count. 4 bonds, 8 electrons. That leaves me with 24 valence electrons to get octets on everything. So let's go ahead and fill in these lone pairs around the oxygens. 3 pairs each. That's 24 electrons total. It looks like I'm done, right? Oxygens all have an octet. Phosphorus has an octet. I've used 24 more electrons. I'm down to 0. Everything has an octet, but I've used all my electrons. And so that usually indicates that I'm done. Okay. 9 times out of 10, when you're doing Lewis structures, you are going to be done in that case. But there are going to be some situations where you actually have more than one option for a valid Lewis structure. And so this gets just one level of difficulty beyond some of our normal exercises in general chemistry. This is one of those cases. I have a valid Lewis structure here in front of me. Everything's got an octet. I used all of the valence electrons, but it's not the best one. How do I determine the best one? Well, the best one is determined based on formal charges. And the idea is that I need to calculate the formal charges for each of the atoms. The formal charge is all for an atom is equal to the number of electrons that atom gets from the periodic table of elements minus the number of valence electrons in the structure that we assign to it. Now, how do we assign them? Well, of course, lone pairs are assigned to the atom that they're on, but then electrons and bonds are assigned by being shared between the 2 atoms. And I'll show you that in a second. Now, so the idea is this, a valid Lewis structure that has the most formal charges equal to 0 is better than one that has more formal charges that aren't equal to 0. Usually we would want negative formal charges to be on the more electronegative atoms. And that means we would prefer that there not be positive charges on electronegative atoms. Well, let's see what we got here. Oh, and the last rule is that formal charges will always equal the charge on the species. And so the charge on the species is 3 minus, so our formal charges should add up to -3 as well. All right, so let's start off with this oxygen in the top right. I have 6 electrons assigned that I would gather from the periodic table of elements. It has 7 electrons assigned in the structure, 6 from the lone pairs. But how do I assign the electrons in this bond? I assign them equally because they're shared. So 1 electron gets assigned to the oxygen and the other to the phosphorus. So that's where I come up with the 7 assigned electrons. So 6 minus 7, that's -1. And of course, we're going to do that with the other oxygens as well. They're all -1. Now, what about the phosphorus? Well, 1 electron shared from each one. 5 from the periodic tables -4, that equals +1. Okay, so I've got a formal charge sum that equals to -3, and that means my Lewis structure is valid, but is there a better Lewis structure? All right, well, let's start over. Let's see if we can come up with a better one. Well, remember that phosphorus can do an expanded octet. So if I take away these lone pairs and I instead make a double bond with them, then I get another situation with formal charges. Now, phosphorus can do this because it can have an expanded octet, So let's then calculate our formal charges and see if we've got a better structure. So those oxygens that have a single bond, they're going to end up 6 minus 7, just like before. So they're all going to be -1 again. What about the oxygen with the double bond? It's 6 minus, how many are assigned? 4 from the lone pairs and 2 from the bonds. So that's 6 minus 6, that's 0. What about the phosphorus? Well, I've got 1, 2, 3, 4, 5 bonds total, 5 electrons minus the 5 that are shared in those bonds gets me a formal charge equal to 0. So I still have all my formal charges equal to -3, but I've got 2 atoms with 0 formal charges, and so that's a better situation. So this is actually a better structure than the first one that we chose based on the formal charge test. So I found the good structure. Of course, I could put that double bond at any location. So that means this is actually a species that exists in resonance. So there would be 3 additional resonance structures, and the real molecule exists in a way that we haven't drawn here as a Lewis structure. We would have to come up with another way to draw it called a resonance hybrid. We'll look at that in another example later. But I've got my brackets around it. I've got the charge around the brackets. So I've got my Lewis structure done. Okay, let's figure out what's up with all these geometries then. Well, I've got 4 geometry groups. Remember that double bond only counts as 1 geometry group. So it's still tetrahedral electron geometry. No lone pairs still means it's tetrahedral molecular geometry. If I look back at the electron geometry to get the bond angle, I come up with 109.5 degrees because it's tetrahedral. Now, just like before, in other situations, when you have an ion, we really don't say polar or nonpolar. It's not applicable. And any sort of intermolecular forces would be considered ion forces. Again, hybridization is just going right back to the electron geometry. This is sp3 hybridized. And counting the sigma bonds, I would count all of the single bonds as 1. So that's 3. And then remember, the double bond has 1 sigma bond. So that's a total of 4. And the other bond in that double bond is counted as a pi bond. So there are 4 sigma bonds and 1 pi bond in the molecule. Okay, that's phosphate.